you raise it, please? Okay. If we consider the charged bosons, deuterons, as a source of screening, then we see a very radical, very unusual, very marked effect. Theory and calculations for a very simple model of these charged bosons, namely that of a charged condensed Bose gas at 0 degrees. Shown schematically here, I have my charged bosons moving in some uniform negative background, which ensures charge neutrality. And these are in the Bose condensed state. The theory shows for this that the radial distribution function G of R is finite at the origin, at R is 0. The radial distribution function tells us about the probability of having two particles separated by a distance R. So G of R being non-zero, being finite at the origin, tells us that the screening is so efficient in this charged boson system that particles can still get on top of each other despite the Coulomb interaction. This does not happen for fermions or for classical particles. It's this phenomenon which I call boson screening. It's a collective effect due to quantum correlations between mobile deuteriums at very high concentrations and in this peculiar energy level structure induced by the lattice. The estimate shown here at the bottom, the estimate of the fusion rate obtained by taking the radial distribution function at the origin, multiplying by the concentration and this constant A, which is the nuclear reaction constant, shows, and this was evaluated for a concentration corresponding to ratio of 0.7 deuterium to palladium. This estimate is enormous, and it's clearly much larger than any of the experimental results show. What does this mean? This is an overestimate induced by the fact that I have taken a model of deuterons moving freely and at 0 temperature. So what we need to do now is to make a realistic model for deuterons moving, go back, back two, another one, back two, please. We now need to go back and do a realistic calculation for deuterons moving in this kind of situation, moving in a lattice with periodic structure with these band effects put in, with electron-deuteron interactions added to add some kind of soft core to the potential, and also at finite temperature. Each of these three factors will cause the rate to decrease, but it will still give appreciable fusion rates at room temperature. Work on this is now in progress. The last one. However, given this general concept, we can already make some predictions. The essence of this theory is that a high concentration of deuterium at room temperatures acts as a condensed charged bosonic system, which has a capability of providing very efficient, and I mean by very efficient, orders of magnitude efficient screening of the bare Coulomb potential. So many reactions could occur in the presence of deuterium at sufficiently high concentrations. So any mixture, deuterium, hydrogen, deuterium, tritium, deuterium, lithium, whatever else the electrochemists want to put inside the palladium, could be screened by this boson effect. And so one would have, provided a sufficient high concentration of deuterium, one could have a whole variety of nuclear reactions. Second consequence, I've said this is a bosonic effect, not shown by fermions or classical particles. So if one takes pure tritiated water, or a mixture of tritium and hydrogen, or pure hydrogen in a metal, then this theory would predict that fusion can occur, provided we go one step further, provided that a pairing of the fermions can take place to form a boson, just as in superconductivity. And these bosons can then condense. So again, we'd be back to this picture, the picture of a collective screening effect induced by a Bose degenerate system. That's all I'd like to say. Thank you very much for your attention.
Before adjourning, I'm certain that you would like to thank all of our speakers